Good day, economists. Today I want to go over how to complete lab assignment number 5. So this is our most recent lab assignment dealing with dummy variables in the model side of our equation. So looking at explanatory variables, independent variables that are also binary or dummy variables, meaning they have a value of 1 or 0. We're going to be using the home price or HPRICE data set and the wage discrimination data set. Both of those are from the COOP textbook and available on Canvas. And this is lab assignment number 5. So I'm going to go ahead and flip it around and get into Stata, and we will get started. Okay. All right, so here we are in Stata. I've actually already imported my data set. I want to go ahead and log this. So I'm going to log it to my teaching file and name it Lab 5. And that will be, I won't be able to do that. Okay, so I'll do it the old-fashioned way. I was trying to cheat. I made some mistakes in the first one, so I had to start over. So let's log this using the name Lab 5. And now I've got my data set already here. So we want to remember that we imported our data set. Our HPRICE data set is our first data set. And we want to make sure that we include the variable names in the first row. And then we want to go ahead and start with problem 1A. And 1A asks us to run a linear regression of sale price on 2 of our first dummy variables. So real quick, let's summarize our data just to remind us of what's in there. We've got sale price is our independent variable, our Y. We have the quantitative variables, lot size, bedroom, bathroom, and stories. Those are X1, X2, X3, X4. And then we have a lot of dummy variables as well. We have driveway is D1, rec room is D2. And then for our purposes in this example, we're going to consider air conditioning D3. And we're not going to use every variable in the data set for this lab, but we'll use a couple of them. So the first thing I want to do is run a regression of sale price on my first 2 dummy variables, driveway and rec room. And then I want to interpret the results. So I have the marginal effect of driveway on sale price is not how we interpret a dummy variable, right? It's not marginal. It's either there's a driveway or there's not. So the presence of a driveway is going to tend to increase a home's sale price by $21,000. The presence of a rec room is going to tend to increase the sale price of a home by $16,000. So let's interpret our R squared, which tells us that our model explains about 14% of the variation in house sale price. A house with a driveway and no rec room will tend to have a sale price of our constant, which is $47,099, plus the coefficient for driveway is going to be that $21,159, which gives us a total of 21159 plus 47099 equals $68,259. A house with a driveway and a rec room will tend to have a sale price of all of these together, the constant alpha hat plus beta 2 hat plus beta 1 hat. And so that's what we can do here with these dummy variables, is we can basically have 4 different estimates for the sale price of a hat, depending on whether the D's are equal to 1 or 0. And we went through this in lecture. So if a house has both, then we count both coefficients. If it has 1, we only count the coefficient for what it has. If it has neither, then it's just the constant. So a house with a driveway and a rec room is going to have a sale price of about $84,282.68. We're just going to round that up to $84,283. A house without a driveway and with a rec room will tend to have a sale price of, and that's going to be just with the rec room coefficient, that's $16,023, and the constant. So we can say $16,023.69 plus the constant of $47,099.08, or about $63,123. And then a house, without a driveway or a rec room will tend to have a sale price of $47,099. And so with that last one, it's because if there's no driveway and there's no rec room, there's no coefficient included, right? Those dummy variables are 0. 21,000 times 0 is 0, and 16,000 times 0 is 0, so we're left with only the constant. So that's how we can interpret those coefficients, right? Does that make sense? Okay, so the next question, we want to look at a regression with a dummy variable and a quantitative variable. So now we're going to do for 1B a regression of sale price on air conditioning and lot size. And that's our D3 and our X1. And for this one, I want to do something different. Rather than ask you to interpret, I want you to write out the equation, which means I want to see the sort of expressed form of these coefficients, of these estimated coefficients. So what we're really saying here is that the estimated sale price is equal to the coefficient, or the constant rather, $32,692. I want to say 693, plus the coefficient for air conditioning, $20,174, let's say 75, round up, times air conned, plus the coefficient for lot size, which is $5.64. And so what that is, that gives us our explanatory variable as a function of air conditioning and lot size. And then we could estimate those y hats by putting in whether a house has an air conditioning or not and some lot size. And so hopefully that's simple and straightforward, but that's what I'm asking you to do is write out that equation and show us what it would actually look like. 1C is going to ask us to do a much more complicated regression. Now we want to do a regression of sale price on, we want driveway and rec room, and then we want lot size and bedrooms. And we want to talk about interpreting the coefficients, the R-squared, and the statistical significance. So the first thing we can say is that all of our variables are statistically significant, right? They all have p-values below the 1% significance level. Their confidence intervals don't contain 0. We can reject the null hypothesis. The standard errors are low. The R-squared, we can reject the null hypothesis for that because the p-value is below the 5% significance level. The f-stat is large. We can interpret the R-squared, which by now you are hopefully really comfortable with. This model explains about 42% of the variation in house sale price. And then we are going to interpret two coefficients, the coefficient for rec room and the coefficient for lot size. Each additional square foot of lot size will tend to increase sale price by $5.20. Ceteris paribus, holding all else constant. And the same thing is for rec room. A house with a rec room will tend to sell for $10,969 more than a house without a rec room, holding lot size, number of bedrooms, and presence of driveway constant. So far, so good? So that's the first part. The second part, we are going to clear this out and bring in the wage data. So I'm going to import that new data set. This is the wage discrimination data set, and we're going to do some different stuff here because we're going to go ahead and have an interaction term in this part. So this is the one that's a little bit more complicated. So let's get that data set in. Again, I use the data set that has the units taken out, so it's a little bit easier to import because I can just import it with the first row as variable names. I don't have to go in and delete out those variable names. And we want to summarize this data. We're not as familiar with it, but we want to remember that the observations, there are 100 observations. Salary is in hundreds of thousands of dollars. Education is years of education. Experience is years of experience. And sex is 0 for female, 1 for male. 31% of the population is male. And that's actually one of the first questions I want to ask you guys, right? So the first thing I ask you to do in 2A is to basically interpret those summary statistics. So I want to know what the mean salary is. I want to know what the mean education level is. And I want to know what percent of the sample is male. And if you're not sure with this stuff, you can always go to your textbook. Your textbook has this stuff in it. This is taken from the textbook from Chapter 7. And so these are actually referenced in Chapter 7. And so if we go into the book and look at regressions with dummy variables, looking specifically at this data set, we can see that in exercise 7.7, the salary is measured in thousands of dollars. Education level is measured in years of schooling. Experience level is in years of employment. And sex is 1 for male and 0 for female. So we can always use this as a reference. So now I can answer these questions. I want to interpret the mean of salary. And so I'm going to say the mean of salary, 22.41, tells us that the average salary in this sample is $22,410.17. The mean of education implies that the average worker has almost 3 years of education. And then the mean of our binary variable sex, if D equals 1 is male, then that means that 0.31 out of 100 people being either 0 or 1, the mean is 31. That tells us that 31% of the sample is male. Okay? So that's how we can interpret those summary statistics. We could also interpret the mean of experience and say, well, the average worker in this sample has a year of experience, give or take. But the next thing we want to do is go ahead and do question number 2, part B. And this is where we're going to do our first regression. We're going to do a simple linear regression of salary on all of our variables, education, experience, and sex, our D1, D2, or I'm sorry, our X1, X2, and D1. And we get our results. And so now we can talk about interpreting these results generally and answering the question of whether or not we see sex discrimination in this data set. So we can say that our R squared explains 86%, our model explains 86% of the variation in Y. We can also talk about the coefficient. Each additional year of education is going to tend to increase salary by about $500. Oops, that's having fun. Holding experience and sex constant. When we get to talking about, we could also say that each additional year of experience is going to tend to increase salary by about $766, right? And those are both statistically significant, but sex is not statistically significant and it's negative. If we were trying to prove sex discrimination, this data set would not do a good job. It's not significant, it's highly insignificant, right? The standard error is actually larger than the coefficient itself. The t-value is tiny, the p-value is much higher than 0.05, and the confidence interval contains 0. So we can say a couple of things. Sex is not significant for all those reasons I said. It also has a negative sign. And this implies the opposite of what most arguments about sex discrimination might try to say. It says that being male has a negative effect on salary. So it doesn't really help us explain sex discrimination in the workplace, right? And it's not significant. It's highly insignificant. So part C tries to solve that. Part C says, okay, let's go in and generate a new variable, an interaction term. And this is the part that we've spent a little bit less time with. So I'm going to go a bit slower. So we want to first generate an interaction term, Z, which is sex times experience, D1 times X2. So we want to generate Z equal to experience times sex. So the command for that is gen, and I'm just going to call it Z. I'm going to call it, we can call it sex experience, you can call it interaction term, you can call it whatever you want. You get to name it whatever you want. I actually do like to say what it is so I don't forget, especially if you get multiple interaction terms going. And then we define it mathematically. So I take experience, multiply it by sex, and I get my new variable. If I do summary of my variables, we'll see that now we've got this new interaction term where experience is either 0 if sex is 0, or the value of experience if x is 1, right? Because we're multiplying x times d. D is either 1 or 0, so x is either itself, z is either x or 0, right? Does that make sense? If we multiply, and let's write it in here, if d is 1, then z is x. If d is 0, then z is 0. Hopefully that makes sense. If you still have questions about that, please let me know. Please let me know, because this is an important part of this. Now we can run a regression. We can run a regression using all of our variables that we've looked at so far. So I'm going to open up the lab real quick and remind myself what regression we're going to do. We're going to run a regression with all of our variables, and then we're going to talk about if we were to write a short report about the presence of sex discrimination, what would we say and how would it change? So we want to use salary, we want to use X1 education, X2 experience, D1 sex, and Z1 experience times sex. And the first thing we see is that while sex is even less significant now, experience times sex is significant at the 5% level. It's not significant at the 1% significance level, but it is still significant with 95% confidence intervals and then 1% level. However, it's still a sign in the different direction than we expect. Being male is going to decrease salaries by about, it's going to tend to decrease salaries by about $644 holding education and experience. Let me restate that. Remember now, we have this new variable that is experience times sex. So that tells us that the marginal effect of experience for a woman is $1,387. The marginal effect of experience for a man is $1,387 minus $644. So let me write that out for you. So remember, again, these are in thousands of dollars. So I'm going to just calculate this really quick. So for people who are not male, D is equal to 0, and so just this beta 2 shows up. For people who are male, D is equal to 1, and so this beta 2 here and this beta 4 show up. So you get a coefficient, a marginal effect of experience of $1,387 minus, because it's negative, $644. So the marginal effect of experience for men is only $743. Does that make sense? So when we have this dummy variable included, we have it affect, when we create this interaction term, the dummy variable through the interaction term changes the marginal effect of the term we're interacting with. So now the marginal effect of experience is a function in part of whether somebody is male or female. And that's the big thing here. Does it prove sex discrimination? Sort of, yeah. It proves there's a penalty. The more experienced a man is, he's going to have less growth in salary based on experience than a female person would. The coefficient for education stays the same. Each additional year of education tends to increase salaries by about $507, $508. The R squared indicates that our model explains almost 87% of the variation in salary. And the coefficient for sex is even less significant and basically says that there's a penalty. If you're a male, you make $80 less than if you were not a male. So that's how we see that interaction term change our equation. And so we can think about it this way. We have now y of salary is equal to our coefficient or our constant, which is $20,000, give or take, plus, our coefficient for education, which is $500 and I'm going to say $8, plus, our coefficient for experience is $1,387. plus our coefficient for sex, which is insignificant, which is actually not plus. It's going to be minus because it's negative. That's going to be $80. And then the marginal effect of experience, if you are male, is going to be, again, that negative $644 times experience sex, right? So that's our new equation. If D is equal to 1, then all of the coefficients stay in. If D is equal to 0, then Y equals, oops, and I'm going to go ahead and put this in here. Y equals just this, and all of the other stuff falls away. Does that make sense? Hopefully it does. If it doesn't, hit up the discussion thread, let me know, send me an email. Otherwise, that's it. That's lab number 5. Make sure you turn it in. You can close your log then, and we'll be all set. If you have any questions, let me know, and have a great day. Take care, everybody.